Now I'm going to go back in time to the 14th century. And that one's called the Rota De La Manfredina. written by an anonymous composer with the arrangement by Nancy Hurrill, 14th century, so a long time ago. And now I'm going to play Woe Betide They Weary Bodhi, and this was written in 1620, Scotland, and they played the harp on their left shoulder. So I'm going to try it. This is new to me. Okay. And I'm going to, I guess I'm going to go backwards to the 13th century. I'm going to play La Corte Estampi Royal. Yes, during that time, they liked a lot of parallel force in those days. I'm going to go back to revisit Arabesque. Yeah, I'm going to switch levers here. That was by Claude Debussy. This is called There's a Great Big Beautiful Tomorrow.
Thank you so much, Kim.
Thank you, Barbara. I wouldn't have found all that early music without you. If you hadn't told me about the Somerset Harp Festival, I never would have found this music.
Well, thank you
Thank
for
you.
sharing it with us. And was that last piece a bit of slack key?
Maybe I'm from the Philip Balding workshop. That and I wanted to learn to play like that without Barbara either. So thank you. And I was trying to remember all of Ortiz's advice: drop your shoulders, just relax. And
Well, you did great, and thank you so much. I mean, it's really been it was a wonderful concert.
oh,
You
thank
did
you so much.
Somerset proud.
Oh, and thank Reza, thank you so much for working all your magic as well. And Barbara, you're just amazing, all of you guys. Thank you.
Well, thanks again, Kim, and I welcome everybody. I think we're ready to go on our wonderful August 13th, Friday the 13th, no less, meeting of the Orange County Astronomers. In keeping with the date, I suppose. I've had my technical difficulties, so I'm glad to see people reacting as though they actually can hear me, which is different than what was happening about half an hour ago. Anyway, welcome. I am the current president, and you will have a great lineup of other folks, including our illustrious vice president, Reza, in a short time. I would like to mention that even though we are now about 2 months out from when we will start taking nominations, if you are at all interested in perhaps participating in the leadership of the club, which is a real fun thing to be involved in, as anybody on the board can tell you right now, we will be starting to take nominations in October. We nominate or we elect a new board every year. If you are interested, please send notice of that to Alan Smallbone, our secretary, so he can make sure that he gets you on the candidate list. We will start taking formal nominations in October and November, and then the ballot will be closed at the end of the November meeting, and we will go through our usual election cycle, which tends to be a whole lot less acrimonious, shall we say, than what we see on the national stage. And in fact, our whole board experience is a whole lot less acrimonious than what we regularly see on the national stage. It is actually quite a bit of fun. So without more ado, I think I will turn it over to our equally illustrious announcement team. Kyle is still with us. When do you go to college, Kyle?
We go drive back to Maryland next Saturday, so.
It's getting close.
Yeah.
Well, have a really good trip, and I will turn it over to your capable hands.
Thank you. Let me share. Go, and I'll play from stuff. All right, so welcome to the August 13th meeting. Now Cecilia and her crew are going to start this off tonight, so.
Hello, welcome new members. We hope you enjoy this amazing meeting that we all put together. Also, there is an event called OVRO. We will be going this December, and for more information, please contact Doug Millar.
So all star parties are currently on hold along with special interest group meetings. However, there are a couple exceptions to this. The next board meeting will be on September 19th online. The beginners class will be on September 3rd online. And those of you who do attend the Orange County Star Party, the one that's in town, that one may, depending on how things go, start up sometime in September. So check the website if you're interested in that, as there may be a star party sometime in the near future.
Okay, so for our events, like Paloma just said, we did have our first reach for this summer. It was great. We went to OVRO, like she said, and we're gonna have one in December, hopefully, with everything going well. So Helen, Doug, thank you for going. And a lot of the members went this time. I know it was amazing. Something to add about the overall that we had for the outreach? Some of my students were from the school, and it was pretty great. As Doug said, it was one of the best ones yet. And we look forward to more and more people going. They actually, some of the club members did some classes for the rest of us. Helen was doing a lot of stuff. A lot of kids went. And it's cool because school's opening up again. So for the outreach for our club, it happens that we don't have any schedules for August because things are kind of iffy in August. But our first scheduled outreach will be for this September, not October and November. So again, we're going to be email all of you guys who are wanting to participate in that and feel safe enough that you are fully vaccinated to be part of this October, November on-site outreach for the schools in our area. So look for that email in the future.
My name is Galilea, and thank you for all of you being here. And today is going to be a waxing present. Make sure that you go look at the moon and check out the cool stuff.
All right, so the Sirius Astronomer, there are items of interest. If you have anything that you would like to put in there, didn't phrase that well, contact Dave Fisher and send him your items of interest to the email address on the slide, and he will put that in once it's gone through its proper editing. Also, if you would like to get the Sirius Astronomer just in electronic format as it's currently available on the website, and you don't feel the need to keep receiving printed copied mailed to you every month, go on the website or with details in the Sirius Astronomer, and you should find information about how to cancel your subscription of mailed Sirius Astronomers and just access it from the website. And the ANZA site, again, the club is not responsible if you choose to go to ANZA as they're unable to implement COVID-19 guidelines there. If you do have an ANZA site, remember to keep areas clear of weeds, as that'll help with fire danger. And then that's it for the announcements. Chris Butler will be next with the WhatsApp presentation. Thank you.
Fantastic. Good to see everybody. Going to tear through a quick look around the sky here. Give me just a moment to share my screen. What have we got going on in the sky right now? Well, if you see this when you look up at the sky, something is very much wrong, but this is our starting graphic here. Let's see some of the things we can see, and we'll start looking at something that Galileo actually already gave us a heads up on. Oh, I should say first, sunrise and sunset right now. Sunset is at 7:40 and sunrise 7:12 a.m. That between those two times, of course, is when an astronomer's life happens. But now looking at the moon, let's see what's going on. We had the dark of the moon on the 8th of August. That's the favorite time for those who like to look at the deep sky objects when the moon's glare doesn't interfere. But I am with Galileo on this one. I'm a big moon fan. And the next week or so is perfect time to have a look at the moon. So if you're a moon fan, you can see tonight we're between the dark of the moon and August 15, we have first quarter. That's when the moon is half lit in the evening sky. Very convenient for viewing lunar features. And then we're going to swing around to August 22nd for the full moon, and then August 30th for the half lit moon in the morning sky, the last quarter moon. Looking at the planets, let's run down the list and see if some of you have a particular favorite. Looking at Mercury, Mercury is something you need to pick your timing right. You need to find out when it has swung to either side of the sun in the sky, and it is doing that now. This is a good time in the evening to have a look over the next several weeks for Mercury. It will be at its widest separation visually from the sun on September 14th on this orbit. So September 14th, maximum elongation for Mercury in the evening sky. It's not that much now. Right now, it's still quite a challenge to see, but I want to give you a heads up for you Mercury people. Now, next in the list, Venus. For those of you who like Venus, and a lot of us do, bright, brilliant. It's the third brightest thing in the sky, except for the sun or the moon. You've probably already noticed Venus in the evening sky. It is very definitely brilliant to the eyes. To your telescopes, though, it's not very close to us right now. It's still pretty small and is about 3/4 lit in your telescope. Mars is down in the the evening sky, the sunset sky. It's actually seen between Mercury and Venus. Of course, it's not next to those planets. It's back behind them on the far side of its orbit, slipping back behind the sun. So not a good time to look for Mars. It is quite small. For those of you who know the sizes on the planets, Mars right now is 3.6 arc seconds across. So it is tiny and not at its best at all, but you might catch a glimpse of it down there. Jupiter, another story entirely. Jupiter and Saturn both are very well placed. They are rising in the east as the sky is getting dark. Pictures to follow, Jupiter and Saturn very well placed. Uranus and Neptune are morning objects at this time. Both, of course, require a telescope to be seen clearly. And I always include Pluto, just out of sentimental status. Pluto is in eastern Sagittarius, and it is just about as well placed as Pluto gets. So if you're brave enough and you've got a big telescope, you can hunt for Pluto this month. I mentioned the sky after sunset. This view here shows the black area would be the horizon. It's fisheye view. Looking off toward the sun has already just now set, and just set, by the way. The real sky would be quite bright at this point still, with a lot of dusk lingering. But you can see Mercury labeled there in Leo. Next to it, Mars. Back behind it, remember, Mars. And then you can see Venus. Venus is farther from the sun, sets later. It's already visually very evident in the west at sunset. Looking at the wider sky at 9 p.m., we have already the triangle of 3 bright stars, Deneb, Vega, and Altair in 3 different constellations. Call that summer triangle. Out in the west, still very high at 9 p.m., you have the bright star Arcturus in Bootes, the herdsman, driving the Big Dipper, Ursa Major, which is visible just at the top of your screen, into the west. So the Big Dipper definitely still visible. In the far, far west of your view, which is screen right, you'll notice a bright object, unlabeled. That's Venus getting ready to set. On the opposite horizon, the east, basically east-southeast, you will see 2 bright objects, also unlabeled. That's Jupiter and Saturn, more in just a moment. Down in the south at this time, we have 2 of my favorite constellations, the Zodiac constellations of Scorpius the Scorpion and Sagittarius the Archer, the Centaur Archer. There are a whole variety of objects down in here, but first for the beginners, let me mention the shape of Scorpius the Scorpion is very distinctive, and his bright star Antares at its heart is quite bright and also strongly orange in color. So it's very distinctive. If you find Scorpius, follow the curving pattern around like a fishhook down to where Shala is the star at the end, a double star marking a stinger. For Sagittarius, if you want to find it, it has a distinctive teapot shape in the center of the constellation, so have a look at that. There are a lot of things to look at in this part of the sky. It's towards the center of our galaxy, but I will mention one right next to Antares in Scorpius, because it's right next to it. As you can see on the chart, M4, which is a globular star cluster, is very easy to find just to the west of Antares. This is a photograph of it, and you'll notice there are actually 2 of them. So this is also a note for you more experienced observers. The bright blob on the left is Antares. All the way on the opposite, on the right, is M4, which is a bright globular star cluster. But between them, closer to Antares, is NGC 6144, which is often overlooked because of its more spectacular neighbor M4 right next door. So there's a challenge for those of you, even if you've looked at M4 many times, check out the other one too. As far as 11 p.m., looking straight up, you'll see that triangle of bright stars, Vega, Deneb, and Altair. Lots to look at here in the summer triangle and these different constellations. First, let me start you off looking around Vega. Vega has a neighbor just to the west. I should mention it. Early evening, the constellation of Hercules is well placed. It too has a giant globular star cluster in it. In fact, really the best one for us Northern Hemisphere observers, M13. The stars of Hercules aren't as bright, but if you learn to find the keystone constellation pattern, asterism we call them, in the center of the constellation, you can find M13 right there in the keystone. Looking over at Lyra, the lyre or stringed, well, actually appropriate for Kim, stringed musical instrument. The bright star Vega will take you into the area. Notice M57, picture of that to follow. That's the famous ring nebula, and the little trapezoidal pattern right there off of Lyra, it's inside that pattern between the bright two stars at the bottom, so it's relatively easy to find. And this is a picture of the ring nebula. Please bear in mind, through a telescope, it is dimmer. It is ghostly gray donut. You don't see these bright colors in an amateur telescope. The colors are really there. They're just too faint for the eye to see. Next door to Lyra, which you can see on the right-hand side of your screen. If you go just a little bit further east, well, the other corner of the summer triangle, marked by the star Deneb. Deneb is the tail of the bird Cygnus. Cygnus, the swan. Deneb, in fact, in Arabic does mean tail. That's how it got the name. Making this giant cruciform pattern in the sky. The brightest star Deneb, and then the star in the middle, Gamma Cygni, fairly bright. Albireo, though, is a slightly fainter, but still easily naked eye star all the way at the end, marking the star's nose. Something on that in just a moment, because flying out there along the neck of the swan, it's worth it to get to the end, where you will find this. Albireo, in fact, even in powerful binoculars and certainly in telescopes, is revealed as a double star, a genuine binary sun, which is a gold and a blue right next to each other. Very pretty. So there's the relationship of these different constellations. Again, about 11 o'clock straight up, but you'll be able to see them at pretty much any of the middle and early evening hours. Of course, right now we are talking about the Perseid meteor shower. I just came back from the 29 Palms Joshua Tree National Monument area, where last night I had a look. That's when the meteor shower peaked. But you should keep your eyes to the skies if you're in a fairly dark circumstance, even edge of the suburbs, that sort of thing. If you've got fairly good skies, you may see a Perseid meteor come streaking across the sky. One detailed note. You want to wait for the constellation of Perseus to rise above the horizon. That's the direction that the meteors seem to be coming from, and that will occur ballpark of 10:30 p.m. by 11, by midnight. You should be in a circumstance where you might see some Perseid meteor showers over the next few days as the storm or the meteor shower winds down. I did include one spectacular picture of a Perseid meteor. This is not from this year, but it's spectacular. And you see the red things there on the horizon. Those are the rarely photographed enigmatic sprites, which are electrical discharges in the upper atmosphere above thunderstorms. The dark mass down below those things is actually a storm system, and obviously there's lightning going on somewhere unseen underneath them, maybe even over the horizon, but the high atmosphere is showing off its own display. I can't promise any sprites, but you might see some Perseid meteors over the next day or two. Down to the south, Jupiter and Saturn, both very bright. Saturn in Capricornus, Jupiter just off the edge into the adjacent constellation of Aquarius. Both are spectacular in small telescopes. This is a recent picture of Saturn, so you can see how the rings are tilted. Even a powerful pair of binoculars may show you that Saturn is a little bit elongated side to side, and that's the rings you're looking at. But with any telescope, put it on Saturn. It's beautifully placed this month. Good time to look at Saturn. Same for Jupiter. Jupiter rises slightly later, but it's still very well placed and up for most of the night. This is a picture of Jupiter with the bands of clouds on it, and you can also see one of its moons, Io, here. To binoculars, even binoculars, the four largest moons, the Galilean moons of Jupiter, stand out very well. Good time to have a look at them with a telescope or even binoculars. Uranus and Neptune, don't want to leave them out, but you will need to wait a little bit longer. If you look carefully, you will see Jupiter starting to set over in the east on the right of your picture. Neptune follows. Neptune is at its highest in the wee hours of the morning. The dot shown for it is not how bright it actually appears, but is a direction marker to show you where to look with your telescope. Same thing for Uranus. Uranus is over in the Aries area, just barely visible to the unaided eye, but something you really need a telescope to see. And that winds up the show in the sky with the sun starting to rise there. This is a 5 a.m. view. That's plenty to look at. And with all that, you've still got meteors to think about over the next few days. With that, I will wish you all clear skies until I see you next month, and we will take you on towards our the rest of our presentation. Thank you very much.
Thank you very much, Chris. That was a great presentation as usual. Hello, my name is Reza Amir Arjamand, and I'm the Vice President of the club. I too would like to welcome you to the August 13th, 2021 General Meeting of the Orange County Astronomers. Before introducing our speaker of the night, I should emphasize that the goal of our meetings is to promote astronomy to everyone, and hence we encourage you all to ask your questions without any inhibition. However, in order to keep the quality of our meetings, we do not handle questions verbatim. We combine, rephrase, and reorder them to fit the natural flow of the talk. Thus, to get your answer, listen for the concept you asked about rather than your name or your words. And please feel free to use the Q&A button on your Zoom client to ask questions during and after the talk. You can also use the chat section to send us any comments you may have. Okay, as for the speaker of the night, he is a principal research scientist at the Cornell Center for Astrophysics and Planetary Science and the Carl Sagan Institute. He studies neutron stars, works on the forefront of efforts to use them to build a low-frequency gravitational wave detector, and has been in hot pursuit of fast radio bursts, mysterious flashes of radio waves that are coming from billions of light years away. He has a PhD in astronomy from Cornell University, and he was a Jansky postdoctoral fellow at the National Radio Astronomy Observatory in Socorro, New Mexico, and the Harvard Smithsonian Center for Astrophysics in Cambridge, Massachusetts. After a stint as a university fellow at the University of Sydney in Australia and as an astronomer at the Australia Telescope National Facility, he has been at Cornell University since 2009. His work has appeared on the cover of Nature, in the New York Times and Washington Post, and has been picked up by his hometown newspaper in Calcutta, India. Please join me by clapping your hands virtually in welcoming Dr. Shami Chatterjee. Shami.
Well, thank you very much, Reza. Thanks for that very kind introduction. It's a real pleasure to be here. Can you guys see my screen okay and hear me all right? This all sounds good, looks good. Excellent. Yeah, it's a real pity that I'm not there in person, and maybe at some date in the future I will manage to visit one of your meetings. But in the meantime, I'm sitting here in my room in upstate New York. The waterfall you see behind me in my virtual background is 10 minutes away from here. So it really is a much cooler, wetter place than where you all are right now. But anyway, today I'm going to talk to you about some very fun new work that we've been doing. And I'm going to try to keep it at a relatively general level. If some of you want more in the way of technical references or pointers to where to look for more, please ask me afterwards. I'll be glad to point you to it. Okay, so with that said, let's just dive right in. A quick word about me, as Reza said in his introduction. What I work on mostly is neutron stars, radio pulsars, and fast radio bursts. I have been part of I've played a very small role in the Event Horizon Telescope collaboration that made that famous image of the black hole that you see. I have led work that has appeared on the cover of Nature, some of which we'll talk about today. And in particular, I have been working on the interstellar medium for a while, and today's talk is kind of built around that. Even though that's not been one of my primary focuses, it turns out that it all hangs together nicely for that. So before I start, I like to show this one slide. It's from an obscure engraving called the Flammarian Engraving from 1888. And it's this picture of a person poking their head behind the curtain and looking at what makes the world work. And it sort of conveys this idea of the world being this knowable thing. The world is knowable. We just have to work at it. And some of what I'll tell you today, again, it's easy for us to jump to conclusions that are not necessarily what we want to jump to. The scientific method has been this wonderful thing bringing us all this knowledge about the universe. And I would like you all to savor some of it for the talk today. Okay, so the first part of my talk, I want to introduce to you radio pulsars. And the reason I want to introduce them to you is because it turns out to be really important for parts 2 and 3 of the talk as well. So let's start with radio pulsars. And this is one of my personal scientific heroes, Jocelyn Bell, seen here as a graduate student standing in front of what are basically dipoles, old style television antennas. For those of you who have any idea what that is, very old style television antennas, that's basically what her telescope was. It was a field of these huge dipoles, and they were doing low frequency surveys of the sky. And she noticed, this is the original chart recording that is in a museum case at the Jodrell Bank Observatory that I took a picture of. And this is her chart recording. There's literally miles of these chart recordings. And in there's this little squiggle that is now identified as pulsar CP1919. And because she was such a good observer, and because she was so intimately involved with her instruments and she knew what she was looking at, she knew that this was a real signal from the sky, whereas this was just interference and it was not something real. So this is the discovery of pulsar CP1919 as it was known back then. When it was discovered, there were a lot of ideas about what it could be, including the possibility that they had discovered little green men. And the code name for this source for a long time was LGM1, because they soon discovered LGM2 and then LGM3. And at that point, it was pretty clear that no, these were not little green men. This was something astrophysical. So what are these pulsars? Today, we understand that these pulsars are neutron stars. They are what's left behind by the deaths of massive stars. When massive stars blow themselves apart in these gorgeous supernova explosions, and some of you might have seen some of these supernova remnants in the sky with backyard telescopes even. This is a multicolor image made from the space telescopes, and you can see the death of a star throwing out all the stuff that is formed in them, all the elements that are forged. And this is what will make the next generation of stars, and then planets, and then people. As Carl Sagan was fond of saying, we are all made of star stuff. This is the star stuff that is being flung out into the medium that will eventually go to form planets and us. But right at the core, right there, that tiny little dot that you can barely see, that tiny little dot is a 10-kilometer radius star that's left behind. And it is massive. It is about 1.5 times the mass of our sun, squeezed into about 10 kilometers radius and spinning extremely rapidly. And this is a neutron star. Observationally, these were going to be undetectable, except it turns out that because these are very tiny, they have extremely intense magnetic fields. And those extremely intense magnetic fields can accelerate these beams of radio emission. And then each time the neutron star spins, you have this beam of radiation swept across our line of sight. And so each time it spins across, you see a little blip of a radio pulse. And so that's what makes a radio pulsar. So we understand how these radio pulsars, or why these radio pulsars pulse. It's just like a lighthouse that's slowly rotating. We don't yet understand how these radio pulsars shine. That turns out to be a much more complicated and tricky phenomenon. But what you can do is you can take this radio pulse and you can convert this to sound. Okay, it is not a sound that's coming to us through space. We're taking a radio pulse and we're converting it to sound. And then this is what it might sound like. You hear the ticks? And that's just an extremely remarkable thing. What you're hearing there is something 1.5 times the mass of our sun spinning. And as it spins, that beam of radiation is being swept across our line of sight. And you hear those blips. Some of them can be much faster. Here is the Vela pulsar. And again, every time you hear the tick is a full spin of the neutron star on its axis. So these are extraordinary things. And pulsars make for a whole evening's worth of talk. And I'm not going to talk to you very much about pulsars because I have elsewhere to get to, but they're just absolutely, absolutely fascinating things. Now, the important thing, the interesting thing about pulsars that is relevant to this talk is the fact that as they propagate through the interstellar medium, and I'll often use the abbreviation ISM for the interstellar medium, as they propagate, radio waves travel through vacuum at the speed of light. It turns out that the interstellar medium is not quite a perfect vacuum. It's a better vacuum than anything we can do in the lab here on Earth. But it's not a perfect vacuum. And so radio waves at lower frequencies travel ever so slightly slower than radio waves at higher frequencies. And as a result, when the pulse arrives, it is swept. The higher frequencies arrive a little bit earlier, the lower frequencies arrive a little bit later. And this sweep in frequency it follows this equation. I promise this is the only equation in my talk for today. And what it says is that there is this thing called the pulse dispersion measure. The DM is the abbreviation we use. And that only depends on the integral along the line of sight of how much stuff there is. The more stuff there is, the larger the sweep is going to get. Now, again, space is a better vacuum than we can achieve in the laboratory. But there is a little bit of stuff. And because things are so far away, this pulse dispersion measure turns out to be incredibly significant. Now, you might think about that and say, okay, so does that mean that we can take this pulse dispersion, and if we have enough pulsars, can we start mapping out the galaxy like pins in a pincushion? Every pulsar is like one pin stuck into the pincushion, and you have one line of sight through the galaxy. And you can say, how much stuff is there along that line of sight? Can we do that kind of modeling? And the answer is yes, because you might be curious about what the Milky Way looks like. And of course, we live inside the Milky Way. We don't know what it looks like because we are inside it. And we are never going to be able to travel out of the Milky Way and look back at it to map it. But what we can do is we can say, okay, it probably looks similar to our nearest neighbor. This is Andromeda, M31, which you can see with a backyard telescope in the night sky. And in fact, this is an image that's a digital mosaic assembled from a very small telescope. It's one of the best images of Andromeda that's out there. You can use space telescopes to study Andromeda. And so here is the same optical image, but then composites using infrared and X-rays. And you can see in X-rays the bright, hot young stars in Andromeda. You can see in the infrared the dust lanes and the spiral arms. And you can put it all together and you can get this composite view of what Andromeda looks like. And you can say, okay, maybe our Milky Way looks something similar. Can we actually try to figure that out? Notice that it's a disk and it's tipped over on its side a little bit, so it looks elliptical. It's almost circular if we were able to see it face on, but it's tipped on its side. And so here now is a slightly technical plot of all the pulsars that we know in our galaxy and the pulse dispersion measure that we measure for them, plotted as a function of galactic latitude, which is simply the height above and below the galactic plane. And you can see that when we look right in the galactic plane, that's where there's a lot of gas and dust. And so the dispersion measures are high. And then as we look away from the galactic plane, the dispersion measure just drops off. Right? So what you're seeing here is that we live in a thin disk of a galaxy. If you look outside the disk, there's not much stuff. If you look in the disk, there's a lot of stuff. And you can also take these pulsars and you can figure out how far away they are, and you can start mapping out the spiral arm structure of our galaxy. Now, this is a complicated thing to do. It's not easy, but there are models for the electron density distribution in our galaxy, and this is what our models for our galaxy look like. We have multiple such models. Like astronomers build these models, they test them. And you can also make nice illustrations like that of what our galaxy might look like, right? So this is one small application of pulsars, which again are amazing things. And I've spent a significant chunk of my life studying them and using them for various things. But for this one task, there's very few things that can tell you what our Milky Way actually looks like because we live inside the pancake. It's hard to see where the chocolate chips are and where the raisins are in the pancake when you're inside it. And these pulsars, by giving you multiple lines of sight, you can actually start looking at that. So that's very cool. Do we have any questions that I should take right now on this?
Well, maybe one. And how can you elaborate a little bit on the angle? How do you measure the angle of the pulsar with respect to the plane of the galaxy?
Oh, that's just a question of we find where the pulsar is on the sky. And then we know where the galactic plane runs across the sky. And it's just the distance above the galactic plane. So that's a very simple measurement that we're talking about. It's just where it is with respect to the plane of the galaxy. And again, if you go out to a really dark site and you see the plane of the galaxy, you'll also see all the other stars in the sky, which are part of our galaxy, but off the galactic plane. And that's all we're measuring, the distance from the galactic plane. It's just that things get thinner as you move away from the galactic plane. But yeah, good clarification. Okay, so how do we look for these pulsars? We basically go out and we point radio telescopes at random patches of sky and we look for these pulses, right? And while people were doing that, we started finding these mysterious flashes in the sky, which are the second part of my talk. So this is a picture I took of the Parkes telescope when I lived in Australia briefly, complete with kangaroos in front, because that is how the Parkes telescope has to be photographed. And what you're seeing in the upper left is this flash of radio waves that was detected at the Parkes Observatory. This is the first known example of a fast radio burst. Again, there's frequency on this axis, there's time here, and you can see that this is milliseconds. And here's a pulse that is swept in frequency. So higher frequencies get there a little bit earlier, lower frequencies get there a little bit later. And this is just the first of these examples. There are many examples of these now, of these fast radio bursts. So what's special about them is, number one, they are just one-off bursts. They flash and then they're gone. Okay. Number two, there's a lot of them. Given that our radio telescopes see only very small patches of the sky at any given time, The fact that we can detect even a few of these millisecond flashes means that we can calculate what the rate of these pulses is all over the sky. And there's about 5,000 of these popping off all over the sky every day. So imagine you're just standing in a dark place and there's flash bulbs just popping off all around you. And there's 5,000 of them popping off every day, right? And that's what it is. It's just a flash of radio waves and then it's gone. And, okay, so maybe there's some weird thing in our galaxy. Let's step back and think about where these pulses are coming from. I already showed you radio pulsars and how the pulse dispersion measure shows us the plane of the galaxy. If you're lucky enough to be in the southern hemisphere, you also see the Magellanic Clouds. And these are satellite galaxies of the Milky Way. So they're tiny little galaxies that orbit the Milky Way. And in those Magellanic Clouds, we know of pulsars. And when you look at those pulsars, their pulse dispersion measure stands outside the envelope of the galaxy. So you can look at these dots and you can say, those aren't part of our galaxy, right? It's outside the envelope of our Milky Way. These aren't part of our galaxy. And that's perfectly sensible. They're part of the large and small Magellanic Clouds. When you put the fast radio bursts on this plot, this is where they fall. All these red dots are fast radio bursts that we've detected. And you can see that their pulse dispersions make it look like they're not part of our galaxy. And yet, that means that they are coming from unimaginably far away. Because remember, I said the interstellar medium was a better vacuum than we can get in our labs. The intergalactic medium is orders of magnitude emptier than that. And so to get to this kind of pulse dispersion measure, now you're talking about millions and hundreds of millions and possibly billions of light years. And so then you can say, okay, but we can detect it with our radio telescopes. And that means they must be astoundingly bright and astoundingly energetic. And that's where we are with fast radio bursts, right? So I want to tell you the story of a very special fast radio burst because I was extremely involved in this. And this was a fast radio burst that we discovered at the Arecibo Observatory, which, as many of you know, is no more. This is a picture I took of the Arecibo Observatory when I was there in 2011, with tropical thunderstorms rolling in. And here is the fast radio burst that we found. You can barely see it, right? There's lots of interference. This is the burst, and then it's not there for the rest of the band. This was almost thrown out as bad data. And some of us persisted with it, and it turns out to be very, very interesting. Okay, this was one flash and then gone. Can't really do anything else with that. But we kept going back at Arecibo and pointing the telescope in this general direction and looking. And we looked and we looked. And then in an email subject line that has become immortal within our collaboration, a graduate student sent around a minor point of interest. And the minor point of interest was that Arecibo discovered this fast radio burst was actually a repeating source. It was not a one-off source. It recurred again and again and again. Right? So at one stroke, this tells you that whatever is producing this fast radio burst can't be some sort of explosion, because some sort of explosion would wipe out the engine that was producing it. So something else is producing this, right? We don't know what. But the other thing it tells you is, well, this might be a good place to go fishing. Now, the problem with Arecibo is that it was the world's most sensitive single dish telescope, but its beam is a big beam on the sky. And within that beam, there's hundreds of radio sources, thousands of optical galaxies, right? There are hundreds and thousands of these sources. And we know that the fast radio burst is somewhere within these yellow circles, but we don't know which point it's associated with. And so you really need to be able to pinpoint it before you can do anything further with it, like saying how far away is it, where is it, all that good stuff. Well, we went to the Very Large Array, the Carl G. Jansky Very Large Array, which is basically this radio telescope array, which allows you to get much finer resolution on the sky. And we ran this radio telescope array in a way which was basically shocking to the people who were there, because we said we want to make movies of the sky at 200 frames per second. And that is not how you run the VLA. With the VLA, you stare at something for a couple of hours and you make an exquisite map of the sky. We said we don't care about the map to begin with. What we want to do is we want to make a movie of the sky, 200 frames per second. Because remember, we're looking for a millisecond flash of radio waves, right? And so we had to run it as fast as possible. And we wanted to dump a terabyte of data every hour. And when we did this, this was not something that was an easy sell. It was just not an easy sell. And we basically were not successful in our first 10 hours of running the VLA. We just didn't have a burst. We were not successful in our next 20 hours of running the VLA. And as we run this, it's a terabyte of data every hour that we're dumping. And each time we go back to the director and we say, well, we weren't lucky this time, but if we find it, it's going to be really cool. So please give us some more time. And they just took a gamble on us. They were sold by our arguments. And eventually we ended up doing 83 hours of this kind of 200 frames per second observations of the VLA. And in one of those frames, there it was, right? That flash of radio waves that is being found there. And it looks like this because the VLA is this Y-shaped array. It looks like this star for a very technical reason. But that point is the point that's interesting, right? And so right there, we identified exactly where it was coming from. And then we can say, okay, with the hours of VLA data, we can make an exquisitely deep map of the sky. And we can say, where in the sky is that coming from? And it's coming from that little dot, right? And now that we know where it's coming from, well, we can put the whole infrastructure of astronomy to work. Right? So this was a tremendous result. This is a paper that I wrote that went to the cover of Nature. And this is the first time the VLA, the telescope itself, appeared on the cover of Nature. So they got their money's worth out of giving us all this time. Then we went to the Gemini Observatory, and this is one of their very pretty publicity photos of the Gemini Observatory. And now that we know where it is, we can point right at the source, and we can find out that that tiny little speck is the host galaxy of this fast radio burst. It's a tiny dwarf galaxy. And more than that, what we can do is we can put a slit across this to make a spectrum of this source. And the spectrum of this source, this is slightly technical, but for some of you, you will enjoy this. So I'm going to explain what's happening here, okay? This is the dwarf galaxy that we now know is the host of this fast radio burst. And these are two stars in our galaxy. And we place the slit right across them. I'm showing you the spectrum below. So the two stars, the spectrum is smeared out into these lines, these extensive lines. The dwarf galaxy spectrum is this fuzzy stuff. And then this bright blip of H alpha and this bright blip of hydrogen beta. And these two dots, which we know are oxygen, right? So we can identify specific elements in that host galaxy, except they're at the wrong wavelength, right? They are shifted far to the red end of where they should be. And they're shifted for a very simple reason, which is the Doppler effect, which is the same thing that you see when when a siren passes by you on the street or a horn like this. The pitch drops as something moves away from it. And that's what we're seeing here, that this hydrogen alpha signature, which should have been at one wavelength, is in this case shifted far to the red. And so there we know what the expansion of the universe, we can figure out how far away this galaxy is. And so we figured out that this dwarf galaxy is about 3 billion light years away. And this was the first time that a fast radio burst had been pinpointed and had been localized to a host galaxy. And it basically kicked off a whole new field of astronomy. We also figured out, using observations at Arecibo, that this is coming from a region of very intense magnetic field. And that got Arecibo on the cover of Nature as well. I won't tell you much about the magnetic field of this source. What I will tell you is that now, this was in 2016 and 2017. So in the next 5 years, we have now localized many fast radio bursts to their host galaxies. And it turns out that fast radio bursts come from all sorts of galaxies at all sorts of redshifts. They're all over the sky. And what we have started to do now is we can use the pulse dispersion of these fast radio bursts. Because remember, if we go way back when I started talking about fast radio bursts, I showed you this plot. In this dot, let's just think about this dot. That much of the pulse dispersion is coming from our galaxy. The rest of it is coming from the intergalactic medium, right? And so now we can go to all the fast radio bursts for which we have hosts and therefore distances. And we can say, we know how much of the dispersion came from our galaxy. The rest of it must be coming from either the host galaxy or the intergalactic medium. And for the first time, we are now beginning to probe the gas content of the intergalactic medium. And this is where, if you've heard about the missing baryon problem, this is where those missing baryons are. In the gas, in the tenuous gas between galaxies in the intergalactic medium. So this is work that has now revealed to us the intergalactic medium. We still don't know exactly what fast radio bursts are, but there's a good chance that they're actually coming from, in bringing this talk kind of full circle, they're actually coming from ultra-magnetized neutron stars called magnetars. So just like the galactic pulsars, but extremely energetic forms of that. But there's also a possibility that they come from some flavor of black holes, or possibly something even more exotic. We do not know yet, and we are actually working on this right now. But in the meantime, we are also using these fast radio bursts to probe the void between these galaxies. And finding them is an immense challenge. I like to call it, it's not looking for a needle in a haystack, it's looking for a needle in a haystack full of needles. Because it's full of pulses and radio interference and cell phone signals and motorcycles and you name it. There's a lot of crud out there that we have to filter out to be able to find these fast radio bursts. But when we do find them, we can actually study the intergalactic medium with them. Okay, and then the last part of my talk is, before I go into the last part, should I answer any questions right here?
Yeah, there are a few from our own galaxy, since you showed that also. Mm-hmm. Well, maybe it's not directly related to fast radio bursts. So about our location in the spiral arms and how we could be sure where we are.
Yeah, that's a really tough question. It's a really, really tough question. But we have now measured the distance to the center of our Milky Way. And so we know where the center of the Milky Way is, and we know how far away it is. It was not an easy measurement, and that is a wonderful talk in its own right, but now we know where it is. And then we can sort of infer based on many different lines of sight where we are. But we're basically in an unremarkable spiral arm out in the suburbs of the galaxy. Right? We're, again, the Copernican principle. We're not in the center of the galaxy. We're just out in the suburbs in a little quiet neighborhood. There's interesting reasons for that, there's interesting reasons why we would expect ourselves to be in the suburbs of the galaxy and not in the center, which relate to how often gamma ray bursts go off in the center of the galaxy and how they might be sterilizing all life there. And that's a whole other talk as well.
Excellent. And we have other question about these pulsars. So you did mention they come in all sizes and frequencies of pulsating. So somebody's asking about what's the average rate at which these pulses pulse and
right. So the typical the typical pulsar we would say is about once a second. But we know of pulsars which are millisecond pulsars, which are spinning basically almost 1,000 times a second. So they're spinning faster than a kitchen blender running on high. It's kind of mind-boggling to think of that. 1.5 times the mass of the sun, the size of a small city, spinning 1,000 times a second. And we don't yet know of any which are exactly a millisecond, but we know like 1.5 milliseconds we have pulsars, right?
Excellent.
All right.
Thank you.
The last thing I want to talk about today is, remember I said into the void. So, okay, I've talked to you about how we model the galaxy. I've talked to you about the intergalactic medium. What about very close to us? What about our very local interstellar medium? Well, before I show you anything about that, I just want to pull up this picture of, this is the shadow graph of a bullet moving through the atmosphere, through air, and you can see that it produces this bow shock, right? Now, these bow shocks, it's just like the wake of a motorboat, but it's in 3D, right? Or the wake of a jet ski, or whatever it is your favorite thing is. There are neutron stars moving through the medium of our galaxy that produce bow shocks. And this is its whole different talk. You can see there's this beautiful bow shock left behind by a neutron star right there. There's this bow shock that I worked on called the Guitar Nebula. You can pull up pictures online. It really does look like a guitar. The neutron star is right at the tippy tip of the guitar and moving extremely fast. And then there are stars in our galaxy, which here's a runaway star, Zeta Ophiuchus. And you can see that it produces this wake. It produces a bow shock. This is seen in the infrared. So as these stars and neutron stars move through the medium of our galaxy, they produce these wakes. And we believe that our sun is producing a bow shock just like that as well. And the Voyager spacecraft is at the edge of the solar system. The Voyager spacecraft, there were 2 of them that were launched back in the 70s. And I'll talk to you a little bit about something neat that we did with the Voyager spacecraft. In particular, the thing I'll talk to you about is the plasma wave subsystem, which are these 2 antennas. The Voyager satellite itself, it's kind of shockingly large. This is a picture of a full-scale model in the JPL media briefing room. It's a photograph I took, and you can see compared to the size of the chairs how big that thing is. It's kind of startling. Well, it's either very big or very small, depending on where your mental model was. I was expecting it to be much smaller. This was startlingly big when I saw it. But that's the size of the Voyager spacecraft. And the Voyager spacecraft, as you know, were launched in the 70s. They did this grand tour of the solar system. They slingshotted past Jupiter and Saturn on their way out to the outer solar system. And they've given us some of the only views we have of the outer planets still, of Uranus and Neptune. And then Voyager 1 and 2, this is where they're going. And so this is the bow shock produced by our sun as it moves through the medium of our galaxy. And one of the Voyagers, at least, has actually crossed this termination shock and is entering the region we call the heliopause, where we have sort of material from our galaxy and material from our solar wind in standoff against each other. So this is the region that we can actually try to probe with the Voyager spacecraft. And that's something that has been done. In 2019, for example, this is the cover of Nature Astronomy, other people's work, where they concluded that the Voyager was now sampling the heliopause. And we are probing the edges of the very local interstellar medium. So here's a quick 1-minute movie. And again, this is not my work, but it's relevant for something I want to show you. It's the plasma wave instrument, like I said. And this is from 2012 and 2013. So you would have heard that little bit of high-pitched sound. Again, this is not a sound, right? This is a radio signal. It just so happens that the radio signal, if you convert that to sound, is right in our audio band, oddly enough. So we're converting a radio signal to sound, and I don't want you to take away the impression that there is sound in space. It's a radio frequency, which when we convert to sound, it just happens to lie right in the audio band. Let's keep going. And so where you're able to hear the sound, you can convert that to a density measurement for the interplanetary interstellar medium, basically. And so you can say, okay, we can start inferring wherever we have these little shocks, we can infer what the density is. Now, there have been many more of these events. Those are the two events that I showed you. Those first two events are what you heard there. There have been many more of these events. And what you're seeing there is basically bursts from the sun overtaking Voyager. And as they overtake Voyager, you basically get this plasma wave oscillation. And that's what you're seeing here. Now, one of our very smart graduate students has actually made a remarkable discovery just a few months ago. And what she discovered is that between these events, where there are these solar blobs of plasma overtaking Voyager, between those events, you can actually see a very faint but continuous signature. And again, we don't yet understand where it is coming from. But what this means is that now we have not just join the dots kind of sampling, but a continuous sampling of the interplanetary medium and this solar bow shock as Voyager moves out. And so Voyager is still sending back data. It will continue to send back data for at least a few more years as its radioisotope generator fades away. And so we have gotten, and we're going to continue to get continuous monitoring of the density of this medium down to very, very small scales. And the small scale, it turns out, is 4.5 million kilometers, but that's very small when we're talking about distances in the solar system. So down at those scales, we are going to get these measurements. Now, this, again, was picked up by the media as a persistent hum in space, an eerie hum, possibly even an ominous hum. I don't know if you thought that the hum was eerie or ominous, but it is persistent. And so this is basically where we are. This is work that is appearing on the cover of Nature Astronomy as of this month, actually. So it is hot off the presses. Okay, that's really all I wanted to talk to you about. I've led you through this little journey, all starting with the idea that these radio pulses are dispersed as they travel through an ionized medium, so that we get higher frequencies a little bit earlier, lower frequencies a little bit later, and we can use this delay, we can use this sweep to infer how much stuff there is between us and wherever the wave is coming from. And with pulsars in our galaxy, we can use that to map out the Milky Way. With fast radio bursts, we can start probing the intergalactic medium. And then with Voyager, we have found a new way to continuously monitor the density in this heliopause or this very local interstellar medium. And so there's surprises everywhere, and we continue to learn. And that's all I had. Thank you very much.
Thank you very much, Dr. Chatterjee. That was an excellent talk, very much enjoyed and well understood. That was great. Thank you very much. You're a great science communicator as well. Let me start by questions and call everybody to type in their questions. The very first one is that, first of all, because in your introduction, I also mentioned that you worked with the LIGO. So one of the things that you did was, you correlated.
I don't work with LIGO. I work with gravitational waves, but not LIGO. We are using pulsars to build a gravitational wave detector for very low frequency gravitational waves. And that's a whole other talk, unfortunately. That is actually a really interesting talk, but a whole other talk. But go ahead.
Thank you. Yes. So thanks for correcting me. And the question is, so you tried to correlate this radio burst with the actual host and visible spectrum. And what other correlations have you been able to make? What other kind of data are you able to have? For example, mentioning gravitational waves. Have you been able to detect simultaneous gravitational waves from the same region of the star?
Right.
Anything in the visible spectrum or other kinds of data?
That's a great question. And astronomers these days, we really do like to do multi-wavelength astronomy, where the analogy is like, imagine listening to a symphony by Beethoven, but all you can hear is the middle C, and you can't hear anything else. It's not the whole effect. And so for the whole effect, we like to observe at infrared, radio, X-rays, gamma rays. Pulsars, neutron stars are visible in all of these bands, depending. In fact, optical is the one band where they're somehow the least interesting. But we do X-ray observations, radio observations, gamma ray observations of neutron stars. For fast radio bursts, so far, we have not found any counterparts other than the radio emission. And that's in part because radio emission can travel through the voids between galaxies and not be absorbed, whereas brief flashes of X-rays or optical light would be absorbed in these immense distances. So it's much harder to actually detect them with the very short flashes so far. We don't yet have any gravitational waves coincident with fast radio bursts, although people have looked for that as well. We do have gravitational waves that coincide with mergers of neutron stars in other galaxies, but again, different story. Yeah.
Great. And if I can have you stop sharing so everybody can see you full screen.
Sure.
That would be great. Thank you. And next question, because we do have a lot of radio ham operators in our club, people want to know the frequencies at which they can observe some of these phenomena, and if they are strong enough that can be picked up by handmade antennas at home.
Yeah, alas, there's good news and bad news. The good news is you can observe radio pulsars right across the radio spectrum, like all the way down to 80 megahertz, all the way up to 5 gigahertz. Right? It's broadband in that sense. The bad news is they're pretty faint. Even for the brightest pulsars, I'm going to guess you're going to need a substantial dish before you can detect it. Although I will say places like LOFAR or LWA, they've been building these tiny little stations. And with several hundred of these tiny little stations, you can detect pulsars. But no, it's tricky. We do use fairly large radio telescopes to detect most of them. Yeah. At Cornell, we have a teaching radio telescope, which is actually an old satellite dish, which is about 5-ish meters in diameter. And it's on our roof. It's a repurposed satellite dish, but that's not big enough to detect individual pulses from pulsars. It is sufficient to detect the galactic hydrogen as the galaxy passes overhead, but it's not sufficient to pick out individual pulses. I see a quick question about what is the speed of pulsar radiation. It's the speed of light. Its radio waves travel at the speed of light. And like I said, the intergalactic or interstellar medium is not a perfect vacuum, so it's not exactly what the speed of light would be, but it's very, very, very close. It's almost unmeasurably close to, like, it's very hard to measure the difference. So yeah, it's the speed of light.
And elaborating on the same question, do these objects, some of them used to be stars, move differently in the sky in terms of the speed compared with the other stars around them?
Right. So I showed you some of these bow shocks that are left behind, that are produced by pulsars. The reason they produce these bow shocks is that they're moving supersonically in the interstellar medium. And so, yes, because these pulsars are produced in supernova explosions, some of them are traveling with quite high velocities. So the Guitar Nebula pulsar, for example, is traveling at over 1,000 kilometers per second. The typical velocity of stars is of the order of like 10 to 100 kilometers per second. So some of these neutron stars are much, much faster than that. Even so, in terms of watching them move on the sky, the movement, because they're so far away, the movement is tiny, tiny fraction of an arc second over years. So as part of my PhD thesis, I actually measured the movement of these pulsars over time. And to do that, I had to use a continent-spanning array of radio telescopes. I used a very long baseline array. And that extends from Hawaii all the way to the US Virgin Islands in the Caribbean. It's a continent-spanning array, and that's what you need to be able to watch them move over at least graduate student lifetimes.
Great, thank you. And so you mentioned this was the first time or the first method that scientists were able to probe not only the interstellar medium, but the intergalactic medium. Are nowadays any other methods, any other frequencies that they can observe and you could compare your work with them? Or is that the sole way?
Yeah, probing the intergalactic medium is a hard problem. Probing the interstellar medium, yes, there's lots of probes because we have stars, we can sort of use indirect probes where the star is lighting up the gas along the line of sight, and so you can probe the gas along the line of sight, we can do that. Probing the intergalactic medium is very, very hard, and there's really no other direct probes of the intergalactic medium. There's some plans to use some X-ray spectral lines. Nothing really, this is really the first time that we've been able to make a direct measurement of the intergalactic medium. That's why the fast radio bursts are so remarkable. There aren't any other direct probes of it.
Okay, great, thank you. And we have a Cornell fellow.
Okay. What's my vintage at Cornell? I was a graduate student at Cornell. I was not an undergraduate, but I started as a graduate student at Cornell in 1996. Yeah.
Okay, great, thank you. And I see, Helen, you have a question you would like to ask? Yes, if you can unmute yourself.
Sorry, do you want me to ask it directly? I was
sure.
I was going to ask, is the rate of the spin of the pulsars related to its mass?
That's a great question. And the answer is no. It is related to, we think, the mass of the star it came from. Because it's conservation of angular momentum that is giving the pulsar its spin. And so what you can imagine, it's just like a skater, and when the skater draws their arms in, they spin faster. It's like that when the core of the star is collapsing, it spins faster. And so you start with the rate that the star's core was rotating at. The star's outer layers are blown off in the supernova explosion, but the star's core has a rotation rate. And then as the core collapses, it speeds up immensely because of this conservation of angular momentum. And so that's how you get the typical pulsars. The millisecond pulsars are a whole other story. They are pulsars, they're neutron stars that have actually been fed matter by a companion star. And as more matter falls on them, their spin speeds up to millisecond speeds. Yeah. So it's a complicated relationship, but no, you can't tell what the mass of a neutron star is from its spin. Most neutron stars are 1.5 times the mass of the sun. That's a good number for almost all neutron stars. But the spin rates go from like a few seconds all the way down to a few milliseconds. So they span 3 orders of magnitude.
Thank you.
Okay, and Doug has a question. Yes, sure, Doug.
There we go. A very, 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 very nice talk. I've been trying to follow along. One of the newer gravitational wave experiment designs is to use a nanometer telescope using pulsars. And from here,
yes, it's nanohertz, not nanometer, nanohertz.
Okay.
Yes. So yeah, I'll tell you a little bit about this work. Again, I actually have given full hour-long talks on this, but it's basically what we're doing is by timing some of these pulsars to exquisite precision, like truly exquisite precision, we can keep track of how far away they are. And then when a gravitational wave passes through between us and the pulsar, it causes this slight change in the distance between us and the pulsar, and then a slight change back, right? And if we can do this well enough, we can actually track this slight change in distance between us and the pulsar by keeping track of its rotation rate very, very carefully. The catch is that the frequencies that we would detect this way, the arms of our detector are many light years long. And the wave basically goes up and down over the period of a year, because the gravitational wavelengths are light years in length, and so nanohertz in frequency. Right, so pulsar timing arrays, we will eventually be able to detect nanohertz gravitational radiation, light year long wavelengths. And what produces this kind of wavelength? Supermassive black holes spiraling around each other. Not massive black holes. They have to be billion solar mass black holes as they spiral around each other, produce this kind of nanohertz gravitational wave radiation. So that's a tremendously interesting thing. We're in the process of building this detector by timing pulsars for many years. And keep your eyes on the news the next couple of years, because we might have some interesting announcements.
What level of stability on the radio receivers? Is it strong?
Yeah, it's a very, very hard problem to keep our receivers stable at that level, because we want to be able to time these pulsars to nanosecond precision.
So
right? We want to be able to measure the times of arrivals reliably and have clocks that are stable at the level of nanoseconds over multiple years.
10 to the minus 16th?
Well, nanoseconds over years, whatever will give us that, that's right. So yeah, it's a very difficult problem.
I've been saying, as I've been watching the gravity wave experiments, that not too long ago, maybe 3 or 4 years ago, we were at the same place radio waves were in the 1890s, coherers and dissimilar metal detectors, and we heard kind of everything at once, but yet nothing, because there wasn't anything, but it was very difficult to receive anything. And in rather rapid succession, we went to a level of what I would call crystal sets. And then we went to regenerative detectors. Well, with a nanohertz telescope, suddenly we have enough wavelength to pick up almost everything, and there's likely to be lots and lots of trash, as well as some good signals available as well. Is that a pretty good parallel?
Yeah, that's right. And so with gravitational waves, right now, the first thing we'll probably detect is what we call the background, the stochastic background, which is the rumble of the superposition of all the black hole binaries in the nearby universe.
Yes.
And then eventually in that rumble, we hope to be able to pick out individual sources, but that's going to take years more. So the first thing we will detect is just going to be sort of the gravitational wave static, if you will, at these nanohertz frequencies. It's going to be an immense challenge that way.
One last question.
Yeah.
If I can, I'm sorry to horn in. The Rubin telescope is going to be taking movies every year, and that should be a boon to the to your kind of work, I assume.
Maybe the LSST, what is now the Vera Rubin Observatory, is going to be an amazing telescope, because what they're going to do is make movies of the sky every night, effectively, right? For our kind of sources with millisecond flashes, that's still going to be too faint for that telescope to capture, because they will capture things down to the time scale of fractions of seconds, but not milliseconds. It's just too faint down at that level. So still, for fast radio bursts, radio is going to remain the only game in town for a little while, except maybe for very nearby sources, which maybe we'll get optical flashes out of. Who knows?
Well, we also have had the pleasure and challenge of working with the Owens Valley Radio Observatory on their low frequency receiver. They have two.
Yeah, that's an amazing site, and there's a lot of cool stuff going on at Owens Valley. Absolutely.
We had two problems. One was undergrowth that got into the dipole antennas, and the other was local interference. There was a FM station on the ground, same level, 100 miles away, that was causing interference, and we had to. Another fellow from our club and I, who were radio hams, because we're familiar with that frequency range, went up and helped out a little bit. So it was very, very rewarding, challenging, and cool to be able to.
Yeah, and now, of course, we have, in addition, satellite interference lots and lots of satellites, lots and lots passing overhead. I see a couple of quick questions in the chat. Can gamma rays bursts help us study particular regions of space? Maybe, but it's unlikely because gamma ray bursts tend to be destructive events, and they are definitely one-off events. So you have a flash and then it's gone. It's possible that you could assemble a whole bunch of gamma ray burst spectra and try to do interesting things with it, but probably a hard problem. Do we have any idea about what the intergalactic medium consists of? Well, yes, we do. And the vast bulk of it is just going to be ionized protons and electrons. That's basically mostly protons, some fraction of helium nuclei. That's basically what's in the intergalactic medium, because that's what was produced in the Big Bang. The primary constituents of the Big Bang are hydrogen and helium, and then some of it condenses down to form stars, and that's where all the other elements are coming from. What's left in the intergalactic medium is basically this very diffuse hydrogen and helium. So that's the bulk of the intergalactic medium. Satellite radio telescopes, it turns out, are not a winning proposition. Partly because our radio telescopes, because the wavelengths we're studying are like meter kind of wavelengths or centimeter wavelengths, the telescopes have to be huge. I mean, imagine the size of Arecibo or of FAST in China. These are huge, huge telescopes that we're talking about, hundreds of meters. We can't practically put dishes like that into space. What is actually being talked about a lot is putting a radio telescope on the far side of the moon. And that turns out to be a fascinating idea. It's a concept being developed at JPL, actually, not too far from you guys. It's a fascinating concept. And that maybe that would be an argument if we were to return to the moon and try to do science. We would try to put, in particular, a radio telescope on the far side of the moon, because the far side of the moon, as you know, can be light as well as dark. It's not the dark side of the moon, it's the far side of the moon, which is dark or light depending on whether it's facing the sun or not. But radio observations, it's basically the quietest radio site in the universe because it's shielded from the Earth by the bulk of the moon. So that's an interesting thought.
Thank you. And we have another question. Since you mentioned that these fast radio bursts can be used to measure the density or vacuum densities, let's say, can you give us some numbers on the interstellar vacuum density and intergalactic vacuum density?
Right. The numbers are very low. It's of the order of 1 or 2 protons per cubic meter is what we're talking about for interstellar space. And for the intergalactic medium, it's orders of magnitude less than that even. So 0.02 electrons per cubic centimeter is a number that we talk, for example. A few atoms per cubic meter. And that's startling when you think about the fact that there's like 10 to the 23 atoms in like this volume of air or something like that, that I'm waving my hands around in. 10 to 10, like 1 followed by 23 zeros. Whereas in space, in interstellar medium, we're talking about 1 atom in that volume, kind of. So very, very empty. And the intergalactic medium is orders of magnitude less than that. Again, until fast radio bursts, we had no measurements of what the real density was. And we are getting the first measurements now, as I showed you in that graph of fast radio burst versus distance. Those are the first attempts at measuring it.
Thank you. And we have another question about how the audio is generated, because you specifically mentioned that when they convert that radio waves into audio, they happen to be in the audible range. Do they just do the same frequencies, or don't they just particularly put that, translate it into frequency that's audible?
Right. So there's 2 different things. For the pulsar sounds that I played you, what we're doing is we're taking the amplitude of the radio waves, which is, it's not there, it flashes on, it flashes off, it flashes on, it flashes off. And we're taking those flashes of radio waves and we're converting them to blips of sound, right? So the ticking is what's important there. The tick, 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 tick that you heard, that's the rotation of the lighthouse beam, right? So there, the frequency of the sound, the ticking of the sound has to do with the rotation of the neutron star. The timbre or pitch of the sound has nothing to do with it. For the Voyager data that I showed, Voyager is actually operating at very low radio frequencies in the kilohertz regime. And so those frequencies do actually happen. If you take those radio frequencies and directly transfer them to sound frequencies, they do just happen to lie in our audio band. So there, the pitch actually does correspond to the radio frequency. It's just a translation from radio frequency to sound frequency. And I realize that's confusing because I'm mixing two different things, but yeah, unfortunately, being a radio astronomer, that's one of the occupational hazards.
And speaking of the Voyager data, so you mentioned that was solar wind particle overtaking Voyager. How do we know it's not the other way? Maybe interstellar medium particles coming our way?
No, we can actually trace this with solar activity. We can literally track coronal mass ejections and see them flying off into space. So we know what they look like, and we know that those are the kinds of things that are overtaking Voyager. So we know that those blips that I showed you are from coronal mass ejections that happened far in the past, basically, that are overtaking Voyager now. Voyager is still on the inside of the solar bow shock. So as it works its way through the bow shock, we're going to start getting more interstellar medium, but nothing yet. So far, we're in the solar wind, the edges of the solar wind. Yeah.
And speaking of Voyagers, usually Voyager 2 is the one that's in the news, but I noticed that you were mentioning that Voyager 1 data, you're getting it. So
yeah, Voyager 1 is a little bit further into the heliopause. And so that's why Voyager 1 is the data that we've looked at so far. Yeah.
Okay, great, thank you. Oh, I see a couple of more questions.
I have indeed visited the Giant Meter Wave Radio Telescope in Pune. Again, astounding facility, and it's an array of dishes, just like the VLA that I showed you, but operating at much lower frequencies. Are there any probes that will explore the area that Voyager is exploring? Not very likely at all, because Voyager was launched in the 70s, and it's taken like 30 plus years, 40, 50 years now to get to where the Voyagers are. Even if we launch probes today, for example, New Horizons, which was just an express mission to Pluto and the outer planets, we wouldn't send it in the same direction. They would go somewhere else. The direction the Voyagers have ended up in is purely an accident of geometry of where Jupiter and Saturn were with respect to the Earth for when they were launched, right? And so there was this possibility of a grand tour that was realized actually by a graduate student for his thesis, that you could launch a mission that could go visit Jupiter and then visit Saturn and then visit the outer planets. And it was this rare alignment. And so the Voyagers were sent off to do that. And so they're just going in one direction. There's no reason we'd ever send a probe in that particular direction ever again. It's just space is big and empty, and there's just a lot of it to explore. So yeah, this is our one shot at that line of sight. But other lines of sight, maybe there is a mission called mission concept called the Interstellar Probe, where the idea would be to send a probe just at very high speeds with the goal of actually going through this and into interstellar space. Who knows? I'll probably be retired by then.
Okay, excellent. Thank you. We have another thing. It's more of a comment, but let me turn it into a question. So they're talking about the gamma ray bursts. So first of all, some of them do have permanent direction rather than spinning. Is that correct?
No, gamma ray bursts, the extragalactic gamma ray bursts are one-off things because they're produced in these hypernovae that are destroying the stars that they're at. So a gamma ray flash is a one-off event. There are repeating gamma ray sources within our galaxy, and they are in fact magnetars. They are these exotic neutron stars that I talked about. And they do produce repeat bursts. And that's why we do think that some of these fast radio bursts are produced by extragalactic versions of these magnetars. Again, I didn't get into talking about what fast radio bursts are produced by, because for this talk, I was just focusing on the void, the medium, rather than the probe itself. But yeah, they're fascinating things.
Okay, excellent. Thank you very much. I've covered all the questions, and that was great. Again, thank you very much. And we very much would like to have you back again in the future, hopefully in person,
Yes.
to update us about all the great work you're doing and all the other talks you mentioned that they merit their own time.
Yes.
Okay, with this, I would like to thank everybody for attending, and please check the calendar on our website for all our upcoming events at ocastronomers.org. Thank you for joining us, and have great times ahead of you. Bye, everybody.
Thank you very much for having me. It was a real pleasure.